G'day everyone, and welcome to chapter 16 on the normal distribution. Okay, let's go. Alright, so the normal distribution. Yes, it is very common. Let's have a look at this first example of heights of people and think about what a graph of the distribution across the population might look like. On this axis down here, what we might have would be the heights of people. Now, let's say we're talking about adult people, so let's say we're talking about, I don't know, let's be conservative, go from 100 centimeters all the way up to, you got your little freaks in basketball, and they might be 200, 300 centimeters, let's just say 300 centimeters. That's pretty tall. Don't know if there's actually anyone that tall, but what you might find is that when you looked at a graph of how many people fall into those categories, starts off very small there, gets very big around the middle, and then comes down like so until you get up to these really tall basketball type people. But most of the people would be in that little section in the middle there. And so what we notice is that the distribution is symmetrical around about the mean, and we also notice it has this kind of bell-shaped curve as well. And here we see a much nicer graph than the one that I just drew, and importantly, we notice that with a normal distribution, the mean, the median, and the mode are all the same. Let's consider the mode, for example. The mode is the most common value. Look at that one there. It's just right in the middle. So yes, we say that the mode is that middle value. The median means that 50% are greater than it, 50% are less than it, and so yes, we see that that would be falling into what we might expect as well. And with the mean, the average value, that's when we add all the values together and divide by how many there are. That turns out to be in the middle as well. So in this case, we'd say the mean would be equal to 0. Other thing is, almost all values are within 3 standard deviations of the mean. Now you'd already be quite familiar with this. PR, what is it? Mean minus 2 standard deviations less than or equal to x less than or equal to mean plus 2 standard deviations is equal to 0.95. Well, that's quite significant proportion of the population, but what that's saying here is within 3 standard deviations of the mean minus 3 standard deviations less than or equal to x less than or equal to the mean plus 3 standard deviations, they're saying it's almost all values are going to be between them. More on that later. And so here we have the official definition of the rule for the general normal probability density function, and there it is there. Quite a complicated thing. In practice, we don't really use this very much. We do use this part in here, the x minus mu over sigma. I'll tell you more about that later. But generally speaking, if you looked at the symbols that you see in here, you notice you've seen that symbol before. That's our standard deviation symbol. Pi is obviously familiar to you. And up here we've got our symbol for the mean. And so those symbols there are not ones that you haven't seen before. It's just the formula itself is quite complicated. Now, as it turns out, it does say that it's a probability distribution function, and this means that the area under the curve must be 1. And if it's 1, that means you can use integrals in order to work out probabilities because you'll be finding out areas. Well, we actually don't do that. What we do is we use functions on our CAS, and that makes life much easier for us. Trust me on that one. Quite often we're going to see the word standard written before normal distribution, and you might have thought, well, standard, it's just like a normal thing, but the word standard actually has a meaning. It means that the distribution has been standardized. It's been standardized so that the mean is equal to 0 and the standard deviation is equal to 1. So when you see that word standard, don't ignore it because it actually means quite a bit to you. So what does it mean in terms of that equation? Well, remember we just said mean was equal to 0 and standard deviation was equal to 1. So in here, if the mean is equal to 0, standard deviation is equal to 1, the whole equation simplifies down to this. Not that that's terribly simple, but it's certainly better than the one you had before, isn't it? Now, if we want to do a conversion from normal distribution to the standard normal distribution, remember as I said in the previous slide, that word standard is actually quite important. So in the standard normal distribution, the mean is equal to 0, standard deviation is equal to 1, and so we might want to have a conversion to do between the two. And the conversion that we use, we say that the letter Z is equal to x minus the mean over sigma. Have you seen that somewhere before? Well, yes, you did. Remember that expression that we had with all the e's in it? In the middle of that, they had the x minus mu over sigma all squared. So, as I said to you earlier, that does become significant, and here is where it becomes significant. So we can use z. By the way, I didn't mention that before. The z is a letter that we use to denote standard normal distribution. So anytime we see the letter z, we're automatically assuming that we're talking about a standard normal distribution. So as soon as you see Z, it means standard normal distribution. And so here's a quick example where we need to do our conversion. So we want to convert this into a Z value. Remember, the Z value means it's a standardized normal distribution. So we've got our rule that says Z is equal to x minus the mean over standard deviation. What we know is the x value is 18, we know that the mean is equal to 20, and we know the standard deviation is equal to 5. Now 18 minus 20 is negative 2 over 5, and there we have it. So in much neater writing, it would look like this. And we still get the same answer, it just looks a little bit neater, doesn't it? So now we're comparing two different normal distributions. Now if you look at the actual overall shape, they look to be pretty much the same, don't they? In other words, the area under here looks to be the same as the area under there. We know they're both equal to 1, but we can see that the spread is the same with both of them. So where the spread is the same with both of them, where they've got the same width and height, we say the standard deviations are the same. So here we would say standard deviation of 1 is equal to standard deviation of 2, the second one. What we do notice, however, is that the means are different. We notice the mean for 2 is actually to the right of the mean of 1, in which case we would say the mean of 1 is less than the mean of 2. In this one, we notice that the means are the same, but we notice that the red one is more spread out than the blue one. Where the red one is more spread out, that means the standard deviation is going to be higher. So we say the standard deviation for 2 is greater than the standard deviation for 1, or written the other way round, standard deviation of 1 is less than the standard deviation of 2. Okay, so here's a little summary, and so it says here that the area under the graphs is 1. That's because they're both probability distribution functions, and that's one of the key features of one of those, and that is that the area is equal to 1. So if the standard deviation gets bigger, the graph gets wider and gets shorter. Okay, that's it for exercise 16A. Now it's time for you guys to do some work. So it's over to you. And for now, could I just say, may your maths be good maths, and bye for now.